Okay, so we're going to start this video off with a stoichiometry problem. So C10H12 decomposes into C5H6. They give us the density of C10H12 and then the density of C5H6, and then they ask how many milliliters of C5H6 can be produced from 18 milliliters of C10H12. So this is a stoichiometry problem because remember, stoichiometry simply means conversion between different amounts of things in a reaction. So they may actually not give you this chemical equation that I wrote out here. I had to write this in myself. So they said that C10H12 decomposes into C5H6. So that means that we simply start off with C10H12 and it's going to break down into C5H6. So I actually had to add in that 2 there, that stoichiometric coefficient, to balance the equation because we had 10 carbons over here. So I needed 2 times 5, 10 carbons over here. 12 hydrogens over here, so 2 times 6, 12 hydrogens over here. So this is just a fairly involved multi-step stoichiometry problem. We started off in milliliters of C10H12, and if you recall in the previous video, we had to go from grams to moles to moles to grams in order to convert between amounts of different compounds in a stoichiometry problem. This time we actually have to start in milliliters, then we get to grams, then moles, then we can convert to the moles of the other thing, then grams of that other thing, and then finally milliliters of that other thing. So let's fit this into our specific problem. So we started out with a certain amount of milliliters of C10H12. So we'll start off in milliliters of C10H12. Then we know, since we have the density of C10H12, we can change that into the grams of C10H12. Finally, we can change this into moles of C10H12, and then we're ready to change into C5H6. So the only way we can get from C10H12 to C5H6 amount is to cross the mole bridge, right? We need to relate C10H12 to C5H6 based on their molar ratio. And we know in this case it's 1 to 2. Then once we're in moles of C5H6, we simply convert that to grams of C5H6. And then finally what they asked for, milliliters of C5H6. So we always start on the top left of our table with the amount that they gave us in the problem. So 18 milliliters of C10H12 is what we start with up here. And remember, whatever units we have up here, we need to cancel them down here. So we'll put the same units, milliliters of C10H12 down here, and we want to go to grams of C10H12. So we know that there are 0.857 grams of C10H12 per milliliter of C10H12. We got that from here. So we just converted from milliliters of C10H12 to grams of C10H12. Now let's go to moles of C10H12. So now we got to cancel these units out down here, and we're going to moles, and we know that there are 132.2 grams of C10H12 per 1 mole of C10H12. So we got that off the periodic table. You simply do 12.01 for the weight of carbon times 10 plus 1.008 for the weight of hydrogen times 12. Now we are in moles of C10H12. So now we're ready to cross this mole bridge. So we know that for every unit that we have up here, we have to cancel it out down here. So we'll put this unit down here so it cancels out. And then we're going to moles of C5H6. So we know that for every 2 moles of C5H6, there is 1 mole of C10H12. So now we're in moles of C5H6. Now we convert to grams of C5H6. So we'll cancel these units out down here, and we're going to grams. And from the periodic table, we know that there are 66.1 grams of C5H6 per 1 mole of C5H6. And then finally, the final step is to convert these grams into milliliters of C5H6. So again, we'll cancel these units out down here and go to milliliters of C5H6. And we know that from the problem, for every 0.746 grams of C5H6, there is 1 milliliter. And now we have completed our table. We ended up in the units that we wanted, milliliters of C5H6. All the other units canceled out. So all that's left to do is multiply across all of the numbers on top. You'll get a number for the numerator. Multiply across all the numbers on bottom. You'll get a number for the denominator. You divide them at the end, and you should get 20.68 milliliters of C5H6. So I hope that made sense. Okay, so here we've got another stoichiometry problem They say stomach acid contains 5 grams of HCl per liter. If a person produces 700 milliliters of stomach acid per day, how many antacid pills, if they each contain 300 milligrams of aluminum hydroxide, are needed to neutralize 1 whole day's worth of HCl? So they gave us the total balanced chemical equation here, so that really helps us out. And the first step here is really to recognize that this is a stoichiometry problem because we're converting between 2 different amounts of 2 different things in a reaction. So we started off with some information here. They say stomach acid contains 5 grams of HCl per liter. So really what that is the density of the HCl in grams per liter. Then they give us an initial amount of 700 milliliters of stomach acid. So that means we started out with 700 milliliters of HCl. And then they're simply asking how many pills, if they each contain a certain gram weight, 300 milligrams or 0.3 grams of aluminum hydroxide, do we need to completely react with all of that HCl or completely neutralize it? So again, we start with milliliters of HCl because that's what we were given, 700 milliliters. And we know the density, 5 grams per liter, so we can convert that to grams of HCl. Then we can go to moles of HCl because we can find the molecular weight of HCl in the periodic table. Then we can cross the mole bridge, go to moles of aluminum hydroxide, and then finally grams of aluminum hydroxide. And once we have that, we know how many grams are in 1 pill of aluminum hydroxide, and we can get to the number of pills. So whenever you set your table up, you want to put the initial information you were given on the top left, and that was 700 milliliters of stomach acid per day. So we'll put that right there, 700 milliliters of HCl, and then we'll convert that to grams of HCl. And we're given the density 5 grams per liter. So we've got milliliters of HCl up here, so we'll cancel that out with milliliters of HCl down here, and we want to go to grams of HCl. And they told us that we had 5 grams per liter. So now be very careful here because we had milliliters of HCl up here, so we need milliliters of HCl down here as our units. But 1 liter is 1,000 milliliters, so be very careful there. Okay, now we're in grams of HCl, so now we'll move on to moles of HCl. Well, we know from the periodic table that HCl has a molecular weight of 36.5, so we're going to put grams of HCl down here to cancel these units out and go to moles of HCl, and we know that there are 36.5 grams per 1 mole of HCl. Now we're ready to cross our mole bridge. So now we're going to moles of aluminum hydroxide over moles of HCl to cancel these units out. And we know that for every 1 mole of aluminum hydroxide, there are 3 moles of HCl. So that's the mole bridge conversion factor, 1 mole of this for every 3 moles of this. Then we'll go to grams of aluminum hydroxide by finding the molecular weight on the periodic table. So again, we got to cancel out these units, moles of aluminum hydroxide down here. And we're going to grams of aluminum hydroxide, and we find that aluminum plus 3 hydroxide groups weighs 78 grams per mole. Then finally, we're ready to go to number of pills. So whatever the number of pills is, remember these are the units that we hoped to end up with. So we're looking for this number here. We know that we have to cancel these grams of aluminum hydroxide out down here. So we'll use these units, and we know that for every pill there are 0.3 grams of aluminum hydroxide. So again, be very careful here that you're using the same units as you did in the upper left corner. So grams of aluminum hydroxide, they said 300 milligrams of aluminum hydroxide per pill, so we'll change that to grams. So 300 milligrams is 0.3 grams. And so then we'll get number of pills. So when you multiply out all of your numerators, you'll get a number. Multiply out all of your denominators, you'll get a number. Divide the top by the bottom, and you should get 8.31 pills. But you know, you can't really take 8.31 pills unless you've got a really fancy pill cutter. So you really need to take 9 pills if you want a whole number. So really, you're going to be popping these antacids, you know, all day. So some pretty serious heartburn. But I hope that made sense. Okay, this problem deals with limiting reagents, yield, and excess reactants. So in order to solve these sorts of problems, you have to use stoichiometry. So I've written the overall chemical formula for this reaction up at the top of the board. And we know that 20 grams of sodium and 20 grams of aluminum oxide are what we begin with, and they're simply going to react until one of them is used up. So the one that's used up first is going to be the limiting reactant. That is actually the definition of the limiting reactant or reagent. It's simply the one of the reactants that is used up first and stops the reaction. So the first step in any limiting reactant problem is to convert to moles from grams if you started in grams. So we started with 20 grams of sodium, so we'll change that to moles of sodium. So we want to leave the units that we're leaving behind on bottom so they cancel out, and we'll go to moles of sodium, and we know that there are 23 grams per mole of sodium. So that gives us 0.87 moles of sodium. So we'll leave that there for now, and then we'll do the same thing for the aluminum oxide. So we started out with 20 grams, and then we know that 102 grams are in 1 mole of aluminum oxide, and this is the way the units have to cancel out. We end up in moles, and then we get 0.2 moles of aluminum oxide. So this means that we started out with 0.87 moles of sodium and 0.2 moles of aluminum oxide. So a common mistake here is to directly compare these amounts of moles and say, well, I have less moles of aluminum oxide, so that means I must have run out of them first, right? Well, actually, you have to take into account these stoichiometric coefficients. So here's a 6, here's a 1. So 0.87 over 6 is actually going to be the final number that we have to compare to 0.2 over 1, or 0.2. So now, once we divide by their stoichiometric coefficients, we can compare them and see that 0.145 is less than 0.2, which means we must have run out of the sodium first. So that means sodium is the limiting reactant or the limiting reagent. So that's how you do any limiting reagent problem. That's how you can figure out which one runs out first and stops the reaction. So number 2, what mass of sodium oxide is produced? Well, now we know what's going to limit this reaction, right? It's the moles of sodium, or the grams of sodium. And we already got moles. We know that we're going to use all 0.87 of them, right? Because we use it all up, that's the definition, and it stops the reaction. So from moles of sodium, we can actually find how many moles of sodium oxide we have, right? By crossing that mole bridge. And then once we have moles of sodium oxide, they're asking for the mass, we can simply change that to grams. So we start out with 0.87 moles of sodium. And then to get to moles of sodium oxide, we do this conversion, so we cancel out the moles of sodium on bottom, we're going to moles of sodium oxide on top, and we know that for every 3 moles of sodium oxide, there are 6 moles of sodium. So then, once we're in moles of sodium oxide, we'll then go to grams of sodium oxide. So we've got moles of sodium oxide here, we'll cancel that out with these units down here, we'll go to grams of sodium oxide on top. So we know that from the periodic table, 2 sodiums plus 1 oxygen, 23 plus 23 plus 16 is 62 grams per 1 mole. So once we have our table set up, we're in the desired units and everything else canceled out. We'll do 0.87 times 3 times 62, get a number, divided by 6 times 1, and you should get 27 grams of sodium oxide were produced. And note here that the sodium is what limited the production of sodium oxide. If we had just had more sodium, we could have made more, but this is what limited our reaction. Okay, the final question here is what mass of excess reactant remains at the end of the reaction? So think about which is going to be the excess reactant. Well, excess just means we had leftovers. So if we used up all the sodium, we must have had some extra aluminum oxide left over. But they specifically ask for how much remains. So they don't just want to know how much was used, they want to know how much remains. So first, we can figure out, we already know how many moles of sodium were used up, and from that we can cross this mole bridge and figure out how many moles of aluminum oxide we must have used up if we used 0.87 moles of sodium. Then this will allow us to take the moles of aluminum oxide used up and subtract it from the moles of aluminum oxide that we had in the beginning. And then once we know how many moles of aluminum oxide we had remaining from this subtraction, we can simply change that to grams since they asked for mass. So again, the first thing I'll do is change moles of sodium used up and convert that into moles of aluminum oxide used up. So we'll start with the information we have. 0.87 moles of sodium goes in the top left, and then moles of sodium down here has to cancel these units out. And we know that we're ending up in moles of aluminum oxide. That's what we want. So 0.87 divided by 6, because there's 1 mole of aluminum oxide per 6 moles of sodium. And you should get 0.145 moles of aluminum oxide. So think about what that means. That is simply the moles of aluminum oxide that we used up, right? That's not what they asked for. They asked how much was left. So now that we know how much we used up, we can subtract that from how much we had at the beginning. And we know we had 0.2 moles of aluminum oxide at the beginning. So if we subtract 0.145 moles from that, we know that we must have ended up with 0.055 moles of aluminum oxide. And then once we have that, it's very easy to simply change to grams that were remaining. We'll just change it to grams. So we have to cancel these units out, moles of aluminum oxide on bottom, and then we're going to moles of aluminum oxide on top. So 0.055 times 102 should give you 5.61 grams of aluminum oxide that were remaining. So I hope that made sense. Okay, moving on to a percent yield problem. So I've got a full reaction written out here at the top of the board, and I'm asking what is the percent yield of copper, one of our products, when 112 grams of copper oxide, one of our reactants here, reacts with excess copper sulfide to produce 130 grams of copper. So first of all, what does percent yield mean? Well, percent yield is essentially the percentage of what we actually got over what we would expect. So if we expected 100 grams of something and got 70 grams, then our percent yield would be 70%. So we already have the actual amount of copper that we produced, right? It says it was 130 grams. So we have the actual amount of copper. All we need now is the expected amount of copper. And to do the expected amount of copper, to obtain that, we have to use stoichiometry. So hopefully you guys are seeing now that stoichiometry is not going anywhere. So you really have to learn it. So in order to get to the expected amount of copper, that's going to be grams of copper, we have to use the information that we began with. So they started out with 112 grams of copper 2 oxide, and they said that reacted with excess copper sulfide. So what does that mean? Well, that basically means we're not going to run out of the copper sulfide. We're going to run out of this 112 grams. So however much copper we can make with 112 grams of copper oxide, that's how much we're expected to make. So grams of copper oxide is what we'll start with. So we started with 112 grams of that, right? And we got to cancel these units out down here. And we'll go to moles of copper oxide, because we have to go to moles to cross this mole bridge and get to moles of copper, and then finally grams of copper. So there are 143.1 grams of copper oxide in 1 mole. And then we'll go from moles of copper oxide to moles of copper, and we'll cancel these units out by putting these down here. And we know that there are 6 moles of copper per 2 moles of copper oxide. So then we have to change moles of copper to grams of copper, and you simply look up on the periodic table the molecular weight of copper, and you see that there are 63.55 grams of copper per 1 mole of copper. So when you multiply all of your numerators out and all of your denominators out, and then divide numerator by denominator, you should get in our final units, grams of copper, that we would expect if we started out with 112 grams of copper oxide to get 149.22 grams of copper produced. But we only produced 130 grams of copper, right? So what was our percent yield? Well, we have to do the actual amount of copper we produced over the expected amount of copper we would expect to produce. So then you do 130 divided by 149.22, multiply that by 100 to get a percentage, and you see that we made 87.1% of the copper that we expected to make, or we have an 87.1% yield for this reaction. Okay, so this is the last problem I'd like to do for this video. So this is another percent yield problem. And in this particular instance, we actually have to work backwards. So this can be confusing, but pay close attention and I think we can make this make sense. So I've got a reaction written up here at the top of the board, and I'm asking how many grams of O2 are needed to produce 105 grams of aluminum oxide, our product, if the percent yield is 75%. So just like last problem, we can figure out how many grams of O2 we need to make 105 grams of aluminum oxide just with a simple stoichiometric table like this. But the problem is this table doesn't care about our percent yield. This table assumes our percent yield is 100% and it doesn't take into account that it's only 75%. So we can go from grams of aluminum oxide back to moles of aluminum oxide to moles of oxygen, and then finally to grams of oxygen, and figure out how many grams of oxygen we must have needed to make a certain amount of aluminum oxide. But this table again only takes into account expected amounts. It tells you what you would expect in a perfect world. So we need to first get our expected amount. So our percent yield, remember, is equal to the actual amount over the expected amount. We were given a percent yield and we were given our actual amount that we want, 105 grams. But that's going to be accompanied by this x here, the expected amount. So when we solve for x, we see that when we expect 140 grams of aluminum oxide, we actually get 105 grams. So we need to build into this table an expectation of 140 grams of aluminum oxide, and then since our yield is 75%, that will give us our actual 105 grams that we want. So again, we have to work backwards here. We're starting with grams of product and we need to get to grams of reactant. So in order to do this, we need to cross our mole bridge, right? So we'll start with grams of aluminum oxide, which we found has to be 140. Then we'll go to moles of aluminum oxide so that we can cross the mole bridge to moles of O2. And then finally from moles of O2, we can go to grams of O2. So again, 140 grams of aluminum oxide. We'll change this to moles of aluminum oxide. We've got to cancel these units out, so we'll put grams of aluminum oxide on bottom. And we know from the periodic table that there are 102 grams of aluminum oxide per 1 mole of aluminum oxide. Then we go to moles of O2. So we'll put that up here, and we have to cancel these units out. And we know that for every 3 moles of O2, there are 2 moles of aluminum oxide. Finally, we change moles of O2 to grams of O2. So we'll put that up here, and these are our final units that we want to end up with. So we'll cancel out these moles of O2, those units, and then all we have to do is multiply all the numerators together, and then multiply all the denominators together, divide the top by the bottom, and you'll get 65.9 grams of O2. So I hope that makes sense. I really hope this video helped you guys out. If you have any questions, please contact me on my Facebook page, facebook.com/denovotutoring, and I'll see you guys in the next video. Thanks a lot.